of the chapter and will be really helpful to grasp the concept. Okay, although only basic questions is in the solved exercise need to be done, and obviously the previous year gate question is very important. Hello my dear, I welcome you in this session of Smart Revision through Formulas. I am Pragyabrat Tripathi, Faculty, Department of Mechanical Engineering. So my dear, in this session, one second, I will check the audio and video, all the things. In this session, we will discuss only formula oriented this session. This session is only formulas oriented, okay? This session is only formula oriented, okay? One second. So audio and video clear, beta? Everyone please reply in the comment. Audio and video clear? Audio and video clear, beta? Everyone please reply in the comment box. So reply in the comment box so that we proceed this session. So my dear, there is some approach of this session. What is that? What is that? You have to read this subject approximately 5 times. Approximately 5 times through a different mode while you are studying throughout the concept. Again you have to make a notes. Again you have to solve the PYQ, again you have to solve the standard book example problem, and again you have to solve the material. What we have to provide the material, that material have a level 1, level 2, level 3. Try to solve all the level so that you have to grasp more and more concept in this subject. So what is that, beta? See, during the semester examination, we have not bothered about the very much aware about the very much of the thermodynamics subject. Why? Because in the semester, just the motive of this subject to just pass out, so that after that they have a very difficulty. Why? Because in the gate there are a very conceptual problem they supposed to be asked each and every chapter, from each and every chapter. So so no idea about the basic concept and very deep concept. This subject is easy, yes, when you have to study 5 times. If you study 5 times, this subject automatically you have to very much easy, okay, truly. And you need to study again and again with the periodically, time to time, you need to be study of this one. And you know that the standard book of PK Nag, you have to know that all students who are the mechanical engineering student, these books you are aware. So try to solve the unsolved problem of the PK Nag and also along with the material of IMS, which have in a market, okay. So try to solve that one, and also help the concept of the basic questions in the solved exercise need to be done, and it is not enough. Obviously you have a PYQ question will be help a lot. So this is the basic approach, just how to study the subject. See my dear, each and every subject have its own method to study. So the thermodynamics subject have a different method to study. Why? Because in this subject there is a different law. Many law is there, and accordingly many law there have a standard problem, a very good numerical problem. So try to solve that numerical problem, and in this session we will discuss all the concept related to that problem and also related to the very good with very good example, okay. So what is that, beta? See, the first one, you know that if you start the thermodynamic subject, the first is know that in the thermodynamic subject we have to bother about the concept of energy. So we know already from childhood, from the preparation of the school level, the concept of energy, but this energy are differ from that concept. Why? Because what the energy we have to study is generally in the classic mechanics, that is our mechanical engineering, mechanical energy. But here we have to study the thermodynamic energy. What is the difference between mechanical engineering energy and thermodynamic energy? We will discuss in this session. Okay, so let's suppose there is a channel is there. Let's suppose this is your cylinder, and in this cylinder you have to, what is that? In this cylinder, initially this is our system. This is our system. You know the system and surrounding. So this is our system. Now we want that the system will expand. we want that, see, this is the modeling of the expansion and compression work. So if there is any expanding system or if any compressing system, what is the model of the work? It is not like a mechanical work. It is not like that during the expansion and contraction you have to know the force into displacement, just multiply it and you get the answer. No, it is very difficult, okay? So let's suppose there is any gas confined in the system and that gas will apply the pressure on the piston, okay, on the pressure on the piston, and this pressure is average pressure distributed throughout the piston. So this, what is the force? Force is the pressure into area. Area is the cross-section area of the system. Cross-section area of this piston, okay? So system boundary, this is your system boundary. Now initially the piston, it is at position x, 1. This is the position where there is a start to movement of the piston. Now after expanding of the gas, the piston will reach at a final point 2. So my dear, the standard model of this work is that what is the work during the expansion of the piston? During the expansion of the system, this is the system will expand. So the work, it is nothing, it is your P into dV. dV is what? dV is what? Displacement, elementary displacement volume. This is your elementary displacement volume, very minimum. And if you, what is the condition of this equation? While you apply this equation, what is the condition? Condition is the first condition is very important. That is your, the system is your quasi-equilibrium. The system, it is your quasi-equilibrium. That means the system will follow from point x to point 2 in the quasi-equilibrium process. What is the quasi-equilibrium process? That means a process which have to start from the state point 1 to state point 2 with a very, very slow process. That is your quasi-static process. And if the process is very, very slow, automatically there is a dissipative loss. That means loss due to the friction, that are the major contribution of the dissipation. So that losses we have to neglect in this case, number first. Number second, the fluid which have to taken as a system is a simple compressible substance. What is that simple compressible substance? That means that substance are free from electrical energy, in electrical work, mechanical, electrical, chemical, nuclear, all the work, magnetic, all the effect of this work we have to neglect. That is called simple compressible substance. So this work, so what is the limit, what is the condition? This is your, the work which is a non-flow work. What is the mean by the non-flow work? That means the work associated with the displacement of a moving boundary. Displacement of a moving boundary. This is your work, okay? Now, up to that, there is any problem, please ask me, okay? PM class, yes sir. Soropada, hi. All good, okay. Thank you everyone. So my dear, if we, so the movement of the piston from position x to position 2, what is the work done by the system? Yeah, work done on the system, that is your work W is equal to integration P. See, this is the integration, and integration we have to done integration over the path. So this work is a path function work. Why? Because we have to integrated form. So integrated form of anything you have to integrate. So during the integration you have to take a very elementary part. So elementary things, elementary strip. So you have to take elementary. That means the process is very slow. Now my dear, if you plot this work on the PV diagram, it is look like that. What is this? P and DV. So let's suppose this is your pressure P. Let's suppose my dear. This is your pressure P. Let's suppose this is your pressure P. Any pressure P. This is your pressure. And this pressure is what, beta? This. What is this pressure? You know this. What is this pressure? Please. This. If you anyone ask you what is this pressure? This pressure is your equilibrium pressure. What is that? Good evening, beta. Everyone. Good evening. This is your equilibrium pressure. Equilibrium pressure. That means it is constant, it may not be constant, okay? And this is your change in volume, elementary change in volume, displacement of the piston in the form of volume wise, okay? So This is your work from initial volume V1. What is the initial volume V1? And there is a V2. So this is your displacement volume. This is your displacement. Piston will displace from initial volume to final volume. Now, my dear, how to find this equation? How to solve this equation? This equation is solved only when you have a relation between the pressure and volume. Then you have to solve this equation. Otherwise, you cannot solve. That means these are the not independent, these are the dependent function, okay? P and V are both are dependent function. Now, so if this is your pressure P and this is your volume dV, this is your volume dV. So if we multiply it, that is your area. That is your area of this strip. And what is the area? Area, it is your see, this is del W. Del W. Why del? We have to represent this work either it is in the form of dW or del W. These are the representation. Why? Because it is a path function. It is a path function. Now the process will follow from point 1 to point 2. If we integrate from V1 volume to V2, that is your total area. That is your total area of the system. Total area of this under the graph along a volume projection. Along a volume projection. So initially there is a gas, initial point is here and here a final point. In between that this is your displacement. So you have to take a elemental part of this volume. Now this volume into pressure, that pressure is your equilibrium pressure, multiply it and you have to get the displacement work or a thermodynamic work. Now my dear, this work is a most practical work. Why? Why? Because this work says that I am present. What this work says that, yes, I am present when there is a resistance. When there is a resistance. If there is no any resistance, there is no work of this. That's why this is a thermodynamic force. That means this force, pressure. So pressure into area, that force F. F is what? F is your resistive force. Resistance against the expansion. That means if the piston will move, there must be a resistance. So that, let's suppose there is a pressure here in this gas, there is a pressure, but here there is no any pressure, vacuum. So this work is zero. If there is a vacuum, that means there is no resistance against the expansion. So only displacement is not enough. Displacement against the resistance. Displacement against the resistance. That means any system have a boundary, and if that boundary will displaced against the resistance, then in that case this work will develop, otherwise this work is zero. So that this work are differ from that mechanical work. So this is not a mechanical work. Okay, now, so this is your PDV work. Now my dear, if you see this one from one example, what is the things is that we have to summarize that work done due to the displacement. That means work done due to the displacement. For whose displacement? Whose displacement, beta? Moving boundary. The displacement of a moving boundary. For what type of substance? Substance is what type of the system? Simple compressible substance. That means it is free from all the effect. That means electrical effect, magnetic effect, surface tension effect. If you neglect, in that case, that is called simple compressible substance. Undergoing what process? Quasi-equilibrium process called displacement work. So there are 4 terms. First is the displacement of a moving boundary. Displacement of moving boundary. Moving boundary. Number second, simple compressible substance. Simple compressible substance. Number second, simple compressible substance. Third one is quasi-equilibrium process. Quasi-equilibrium process. And yes, this is very important, this displacement of a boundary against resistance. Against resistance. If there is a no resistance, there is a no any work. Now, so quasi-equilibrium process. What is the quasi-equilibrium process, beta? Please tell me, anyone. If someone asks you what is the quasi-equilibrium process in a single line, just tell me. What is the quasi-equilibrium process? Please tell me. What is the quasi-equilibrium process? Please tell me, beta. Everyone, please tell me. Who are present here, please tell me. What is the quasi-equilibrium process? Please tell me. What is the quasi-equilibrium process? Quasi-equilibrium process is nothing. It is your internal reversible. Internal reversible process. Now, the question comes, ki, sir, how to make the process is internal reversible? How to make the process is internal reversible? The process make to have internal reversible is free constant. No. Internal reversible. Internal. How to make the process internal reversible, Mani? How to make the process internal reversible? Anyone, please? How to make the process internal reversible? How to make the process internal reversible? If you want to that, the process is internal reversible. How to make that process? Practically, how to make? That means movement of a boundary is in a very almost slow process. That means each and every point from point 1 to point 2, each and every from point 1 to point 2, each and every point have a equilibrium point. These all are changes to path is not like that. All the path which is follow from point A to point 2, all the points have a equilibrium points. That's why that is called internal reversible process. Clear? That is your internal reversible process. Okay, beta, correct. Now, so that is your understanding. My dear, one thing is very, very important. I am telling you. I want to that this work, this PDV work is, I give you, I just, why? Because you are habitual with the option. So I give the option 4 option. This work, PDV work is applicable for, these are MSQ type question. This work is applicable, MSQ, more than one option is correct. Number first option, closed system. Number second, open, closed system only. Number second, open system only. Number third, both open and closed. Number fourth, simple compressible substance. What's your option? Option number A, this work is applicable only for closed system. Option number B, this work is applicable for only open system. Option number C, this work is applicable either open or closed system. Number D, this work is applicable for a substance of a simple compressible. What is your option, beta? What's your option? Please tell me. A is only closed system, B is only open system, C is closed and open system, D is for simple compressible substance. These are the MSQ. More than one option is correct. Please tell me. Please tell me, everyone. The option number A, this work is applicable for closed system only. Option number B, control volume only. Option number C, closed system plus control volume, both we can apply this equation. A and D is simple compressible. Okay, so Mani says that Rohan A and D. Rohan says that A and D. Mani says that A and D. Rohan, Mani, you both are wrong. See, that is the beauty of thermodynamics. That is the beauty of thermodynamics. You are wrong. The option is C and D. This is very important thing, my dear. I read. Option is C and D, both. Not A, not B. Clear? Read the statement carefully. See. See, my dear. Read this statement carefully. Read this statement carefully. Read this statement carefully. Very carefully statement. I am telling you, very strong. What is the statement? Work done due to the displacement of a moving boundary, okay, of a simple compressible substance undergoing a quasi-equilibrium process called displacement. There is nothing says that it is for closed system. See, my dear, this work is applicable where the displacement of a boundary takes place. Where the displacement takes place, this work will happen. Either displacement of a boundary of open system will take place, this work is applicable. Either the displacement of a closed boundary, this work is applicable. It is not necessary that it is applicable only for a closed system. I will tell you. Just I will tell you. See, just see, my dear. Just see. Just see. Let's suppose this is your any system and this is your piston. This is your piston. Clear? This is your piston. Okay. Let's suppose this is our system boundary. Let's suppose this is our system boundary. Okay. The mass is in here. Now tell me this is closed system, open system. Everyone please. Tell me this is closed system, open system. Please tell me. This is closed system, open system. Please tell me. This is closed system or open system? Anyone? This is your closed system, open system. Yes or not? This is your open system. Why? Because the mass is in. Now, so mass is in here. Now, due to this mass, this boundary will expand. Why? Because the piston will move up. Move up. So the boundary, this boundary will displace. So this boundary will done the work to lift the piston. That is your displacement work. PdV. Mass flow. So this is your displacement. So in this, though there is an open system, but this work will done. So where? Hi Amit, hi, thank you. So where this work is here, only the displacement of a boundary, either it is a closed system boundary displacement or either it is open system boundary displacement. Where is the displacement? This work will happen. So my dear, 99% student are not aware that sir, this boundary work 1 to 2 is integration V1 to V2 PdV applicable for closed system. This is wrong. This is wrong. This is wrong. No matter what is the system, applicable for both closed and open system. This is very important thing I am telling you. I know that a student in the student community where is the misconception. Yes, That means VD, this is PdV, VDP another thing. This is your PdV beta. VDP, it is your open system. VDP only applicable for open system. Money, you are right. Both are different thing. Acha, what is the difference between PdV and VDP? Anyone please tell me. Yes, you are right. See, work transfer is equal to integration PdV, work transfer is equal to integration VDP. What is the difference? Please tell me. Please tell me. This is a very subtle concept. What is the difference between these two? Please tell me. Just you tell, I will write. What is the first difference? Please tell me. What is the first difference? Please tell me. What is the first difference? Please tell me. This is your, okay. This is your, please tell me, this is your non-flow work. This is your flow work. That means there is a flow, it is here. What does it mean by non-flow work? What is mean by the non-flow work? Please tell me. Work transfer, huh? Change to what? What is the non-flow? It is not like that for closed system. It is not like. It is not like a closed system. No. It is not like a closed system. 90% student says that it's a non-flow, that means a closed system. No. Non-flow, that means here is the no flow takes place. Here there is a no flow takes place. Yes, not like a closed system. Only there is a no flow, that means the boundary will not cross the fluid. Yes. That means the boundary, what your boundary selected, the flow is not crossing. That is called non-flow. But it is not mean that the system is closed. No. System is a flow. So this is your non-flow work. So my dear, this is a very subtle concept. Non-flow work and closed system, these are two different things. Number first. Number second, what is the number second? Please tell me. What is the number second? Please tell me. What is the number second? Okay. This is state point 1. This is a state point 2. This is a state point 1 and this is, and what is the limit here? What is the limit here? Here limit I to E, inlet to exit. That means this work transfer across the section. This work transfer across the section. But this work transfer across the boundary. Yes, this is your boundary. That means initially what is the state point of, that means if there is a system, I have a state point 1. After some time it will expand and it will reach at point 2. So the state point 1 to state point 2, that means this is a state point like V1 to V2. V1, V2, P1, P2, what is that? State point. But this is not a state. This is due to the cross section. That means if there is any fluid or any channel, the fluid is flowing. So you take a cross section I and E. So it is applicable over the cross section and it is applicable over the state point. So this is a cross section and this is a state point. Number first. What is the second difference? Third difference. So this is for the state 1 to state 2. This is for the state, this work transfer from the system is from state point 1 to state point 2. This is work transfer from the system from inlet section to exit section. So these are the section. Now my dear, the second very important. So this is a very important thing. This is the very important inlet, exit, and this is state point 1 and state point 2. This is very important, I am telling you. Now the third difference is, if there is a work output, system, here it is positive, but here work output system must be negative. So for the turbine, this is negative. For the pump, this is positive. In the pump, we have to input the work. So the work transfer is positive I to E VDP. If there is a turbine, work output, so work output here is a negative. So that is the second difference. Change to AC. What is change AC? What is money? Change to AC. What is that? Option. You are telling option. See, that means applicable for both either closed or open system, and second, simple compressible substance. Clear? Clear, everyone, please, clear? So what is the difference between these two work? Clear, beta? Please tell me. Any confusion? Please tell me. If you have any confusion, please tell me. I know that in the YouTube channel, such type of content is not available. Very crystal clear, subtle concept is there. So these are the two different things. And one thing is very important. Non-flow, that means it is not like a closed system. Non-flow, that means what your boundary will select. What is the boundary? If there is a system, and of the system there is some portion of a boundary over which there is no any flow takes place. That is called non-flow system. Clear? And this is for the flow. That means when the flow, that means this is for open system work. This is only for the open system work. At inlet to exit cross section. So limit is your cross section. And here the limit is your state point, initial state to final state. Clear, everyone, please? Everyone clear? Okay. Now next. Okay. So if you have, let's suppose there is any process. Let's suppose there is any process, beta, and the process is generalized process. Let's suppose there is any process. PV per power n is constant. Okay. Let's suppose there is any process. The system is follow PV per power constant. Now this says that initial pressure of the system, let's suppose 3 bar, and volume initially it is your 0.1 meter cube. It will expand to a final volume of 0.2 meter cube. That means system will expand. So system will expand. Determine the work transfer for the process. If you take the n equal to 1.5, n equal to 1 and n equal to 0. Class duration 1 hour only. Okay. Now for n equal to 0, pressure is constant. So there is a constant pressure line. 1 to 2. Volume will change. So there is a V1 to V2. N equal to 1, there is a isothermal. That means PV is equal to constant. Isothermal. N equal to 0, n equal to 1.5, there is a adiabatic. Yeah, polytropic, you can say that. 1.5 is equal to constant. So one is your polytropic, second one is your isothermal, third one is a constant pressure. ADI. Okay. Okay. Now my dear, what is that? How to model this problem? The model is the gas is in your closed system. See, the system is closed. Gas is confined in a system. Adiabatically. Okay. Pressure P1. Polytropic. Yes, this is your polytropic. Not adiabatic. You cannot say that. This is your polytropic. This is your isothermal. And this is your isobaric. There are three processes. So 1 to B, this is your isothermal. And this is your adiabatic. Expansion will take place. See, my dear, in which process the area is maximum? Constant process pressure expansion, the area is maximum. Then constant temperature, the area. This is your pressure constant. This is your temperature constant. And this is your PV pe power 1.5 is equal to constant. Okay, now moving boundary work is only mode of work. Yes. Why? Because this is expansion. There is no any electrical work, no any shaft work, nothing is there. Only there is a moving boundary work. And the expression is a polytropic process. If you substitute work transfer is equal to integration P dV, and you know that, sir, this P is the function of V. So you have the function. First one is, if you n equal to 0, n equal to, this is n equal to 0. In this one, n equal to 0. What is the area? That means, what is the area? Simple. P take outside. V2 minus V1. So you have a pressure. You have a volume minus V1. Just put it. Get the answer. Now, there is an expression for that one. You just expression. So, for polytropic, you have a relation. What is that? P is equal to C by V pe power 1.5. Put here P is equal to C pe power V pe power n pi. Integrate it. That is your answer. Third one, P is equal to C by V. Put here instead of P. Why? Because you have to solve this integration if and only if there is a relation between P and V. Otherwise, you cannot solve this equation. So, all the relation you have made. Clear? Now, next. See, what is this one? Please tell me. All isothermal process. Read this question. This is in the gate. There is a MSQ question. So, in the MSQ, let's suppose there is a 4 statement is given. And they says that which of the following is are true? Is and are true. So, let's suppose there is a first statement. All the isothermal process must be reversible process. Please tell me this is true or false. Please tell me this is true or false, beta. Please tell me this is true or false. Please tell me this is true or false. Everyone, please. Please tell me this is true and false. That are the application. All the isothermal process must be a reversible process. This is true or false? Please tell me. Please tell me, everyone, this is true or false? Please tell me this is true or false? Everyone, please, I give you a challenge. Please tell me. If you give this, and if you correct the option and you have a proper idea, okay, but reversible process is not isothermal there. And what is that? What you say that? True. You say the true. Mani, you says the true. Everyone, please. Again 30 seconds I will give you. Again 30 seconds I will give you. All the isothermal process must be a reversible process. True or false? Mani says that true. Anyone? 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 Anyone other than? It is false. It is false, not true. This is the beauty of thermodynamics, I am telling you. Now, my dear, if I give you, this is the statement false, just think 1 minute. Why it is false? Just think. Why it is false, beta? Just think. अच्छा false है, mistake किया मैं. Okay. How it is false? Please tell me how. This is the big question mark. This is the big question mark. How? I will explain you. See, my dear. What is the reversible process? Must be internally reversible as well as external reversible. Clear? Clear? Now, that means, let's suppose, what is the internal reversible and what is the external reversible? First understand. This is the very important thing I am telling you. What is that? Let's suppose there is a container. In this container, there is a piston. Okay. Now, this is your system boundary. Okay. Now, you have a thermal reservoir, let's suppose, of a, let's suppose, temperature T0. Now you are supplying the heat, let's suppose Q. Now you are supplying the heat from this system, thermal reservoir, to this system. Now, my dear, let's suppose its initial temperature is T1. Let's suppose its initial temperature is T1. Let's suppose its initial temperature is T1. Now, when the heat will supply? When the heat will supply? When this initial temperature is less than T0. In that case, the heat will supply. Okay, now see. What is the isothermal process? What is the isothermal process? Please tell me. Isothermal process, that means the temperature throughout the same. That means T1 equal to T2. This is your isothermal. You know that. Okay, sir, if the system temperature doesn't change, that is your isothermal process. But they says that if you have an isothermal process, how to make the isothermal process? How to make isothermal process? That means while you are supplying the heat, the temperature of the system want to increase. Now, if you maintain the temperature, you just push the piston outside so that the temperature will maintain. Again, you supply the heat. Again, you push the piston so that the temperature will maintain. So the temperature is maintained. So isothermal. Now, my dear, while you are pushing the piston upward to maintain its temperature constant, if you push the piston upward in a very slow manner, that is your quasi-static process. And quasi-static process must be internal reversible. If the movement of this piston is in a very slow manner, why the slow manner? Why? Because you want to that the temperature maintain constant. So the temperature maintain constant, and if the process is very slow, that is called quasi-static process, and quasi-static process must be an internal reversible process. So it is reversible. Now we'll check it is external reversible or not. So if the temperature, let's suppose this is two temperature difference, let's suppose this T0 minus T1 have a finite value. First. Second, if T0 minus T1 is infinite value, infinite a small value, infinitely a small value. If the, see my dear, if the T0 minus T1 is infinitely a small value, then in that case this is an external reversible. But you cannot say that, sir, this temperature is, let's suppose this temperature is 20 degrees centigrade and this temperature is 80 degrees centigrade. So there must be a finite value, that means 60. If this temperature is 20 degrees centigrade and this temperature, let's suppose this is 20 degrees centigrade and let's suppose this reservoir have a temperature 20.0001 degrees centigrade, and if you differentiate these two, there is an infinitely small value. So that maybe depends upon this temperature difference. So isothermal process to may be internally reversible, but it is externally irreversible. Why? Because if the temperature will transfer, the temperature heat transfer will be a finite temperature difference. So no must here is a very important line. Must always, not always. When the statement is the thermal process may it may be internal reversible and external irreversible. So the total process is irreversible process. Clear? Everyone please tell. Sound नहीं आ रहा? I will write up to that